Example 4.6 from the Fundamentals of Fluid Mechanics from Munson, Young, and Okiishi, 8th edition. In this example, we have a fluid flow which is steadily going through a two-dimensional nozzle, which the length is provided by the equation. If we ignore or we neglect the viscous and the gravitational forces, the velocity field is given as the formula is provided, and the pressure field is also provided. The values of V0 and P0 are values at the origin of the nozzle, which it also indicates that the fluid speeds up as it goes through the nozzle. We need to determine as a function of x and y the time of rate of change of pressure felt by the particle as it goes through the nozzle. Okay, so let's start by writing the information that we have. So in this case, we know that the velocity field is simply going to be V0 1 plus x divided by L. We know that the velocity in the y component is simply minus V0 y divided by L. We know that the pressure is simply P minus P naught is minus rho V0 squared divided by 2, and this is equal to times x squared plus y squared divided by L squared plus 2x over L. Okay, and what we're looking for in this particular case is the rate of change of the pressure. That means that we're looking for dP dt, and that is simply dP dt plus u dP dx plus v dP dy plus w dP dz. This case, we are going to assume that the flow is steady, so we have a steady state, and notice that we have variables in the x and the y axis, so it's going to be two-dimensional. That allows us to get rid of this term for a steady state, and the last term since it's two-dimensional. Okay, so in this equation, basically we have already the value of u. We need to calculate the pdx, and we need to calculate the pdy. So we simply calculate the value of the pdx, and we take the derivative of this variable, and once we simplify it and we do a little bit of math, it should give us negative rho v squared x divided by L squared minus rho V0 squared L. Okay, so that's the pdx. If we do the same process for the pdy, so once again we take the derivative, and after we do a little bit of simplification, it should give us negative rho V0 squared y divided by L squared. Okay, so what we need to do now is to substitute into the equation. So we're going to substitute all these values into this equation to be able to get a final result. So I'm just going to maximize this a bit so that I could show you the solution. So we are looking for the pdt, and we're going to substitute first the value of u. So u is simply v naught 1 plus x over L, and then the pdx, as we calculated, is simply minus rho V0 squared x over L squared minus rho V0 squared over L. So that's the first component that we have over here. The second component is v, which is minus V0 y L, and then we multiply it by the p dy, and that is minus rho V0 squared y divided by L squared. Okay, and then if we simplify it, we have that the pdt becomes, so after we do a little bit of simplification, minus rho v to the third 1 plus x over L. This is x over L squared minus 1 over L plus rho v to the third y squared L to the third. So as you notice, this process is very straightforward. You have to write the rate of change of the quantity you're looking for, which in this case is pressure. We write the material derivative. We cancel the information that we need to based on the assumptions, whether it's a steady state, 1, 2, or 3-dimensional, and then carefully calculate each one of the derivatives and then plug in into the original equation and simplify.